This video will be about a very simple and at the same time a very useful, very effective tool to add depth and width and some equalization to our input signal following a natural reference. At the same time, this tool is a first building block of a good reverberator, and that's why I start with it. And it, I guess, requires a little preface. In the second half of 20th century, researchers in the field of architectural acoustics made a significant step towards finding correlation between objective parameters of the concert halls that would be derived from the impulse responses recorded in those halls and the subjective preference for the acoustics of those halls. The task that architectural acousticians trying to fulfill is to get a three-dimensional sound field that people would describe with the beautiful words. Yeah, it's a bit different from what I do, for example, in these videos, and what sound designers do most of the time. Yeah, most of the time it's stereo recordings which are example of an art form in itself. Stereo recording can act as a kind of extract from the three-dimensional sound field, those naturalistic recordings, but at the same time can act as just a picture on the wall with some painting having no reference to the natural world. So there is a question whether we can use the result of those accomplishments in architectural acoustics in stereo recordings, and trying to find the answers to this type of questions, because there are lots of parameters and some of them would work probably, some of them not, because of the limitations of the stereo reproduction. I found the works of David Gressinger, who is a very interesting researcher in the field of architectural acoustics, as well as a very known person for being one of the key people behind Lexicon Company, which was pioneering digital reverberators in a commercial area. So the term early spatial impression comes from his works. It's his term. And he differs in his terminology a bit from most of other acousticians in this area. Why his works are so valuable in the context of the question I put is that he is not only about making good concert halls. More than that, he is probably more into making a good recordings, because, well, the devices that they were making are in the first place the good devices for the stereo recordings. Yeah. So he has, if anyone is interested in these questions, he has all his works published on his website, and they are available for free. And I will put one of them as a reference here. This work is called page 4, It's called The Theory and Practice of Perceptual Modeling, How to Use Electronic Reverberation to Add Depth and Envelopment Without Reducing Clarity. Now, I will put this page as reference because it has what he calls an ideal reverberation. Now, this reverberation profile is not quite a natural one, because usually the impulse characteristic has more reflections in this area. But what he talks about is something that probably would be considered even better than natural reverberation profile. So let's start with his term early spatial impression. What he calls an early spatial impression is the first 50 milliseconds of impulse response, or to be more precise, how the first 50 milliseconds of an impulse response affect listener in natural listening conditions. Of course, in the real space, in the real enclosed space, listener doesn't listen to the first milliseconds of an impulse response convolved with the input signal. He hears all of it, yeah, mixed when every previous signal is mixed. Every next signal is mixed with the previous signal's reverberation tail and all that. So, in this work in particular, as in some other works, he describes all those situations and talks about that. I want to concentrate on his view of those first 50 milliseconds and want to illustrate how it affects the input signal and how we can use it if we want to make a very nuanced spatial processing by adding depth, width, some character, some liveness to the signal, and at the same time without actually introducing the image of space. This is a very, very important task for the stereo recording, because usually we don't want a lot of reverberation tails in our recordings. We can introduce that easily, but usually it's very probably that it will start working as a background noise. First thing he talks about that in this region, as you can see, from 20 to 50 milliseconds, we don't need usually more than 5 reflections. And why 20 milliseconds? This comes from the usual situation with the concert halls. Let's say for 1,500 to 2,000 seats concert halls. The time between the first direct sound, the first thing that comes to the ear of a listener, and the first reflection, and which is called internal time delay gap usually, is usually about 20 milliseconds. Now from this point to this, he talks about 5 reflections. He talks about that it should be about, let's say, twice quieter than the direct sound. Minus 6 dB is about twice quieter. And then he goes on to other things. He goes to what happens after that. This I will say for later. For the next video, I guess I will dedicate 2 or maybe 3 videos on this question. But now let's start with this e.t.c thing. So here's an instrument. It's a very basic instrument. The instrument generates 5 reflections. Each reflection is a mono signal panned with a pan 2 unigenerator, which takes a mono signal as input and returns 2 copies of it with the amplitude panning applied to them. Every reflection has its delay time specified and a bandpass filter applied to it. We have low pass and high pass filter that is applied to the input signal before it's been delayed and filtered by the bandpass filters. In some cases we probably don't need them, but it's a very cheap addition, so in some cases it can really help, because we might like the timbral profile, but we only want to, let's say, diminish the low frequencies or high frequencies a little, and in that case it's a useful thing to have, very cheap. Okay, now let's take a listen. Here's a dry signal. It's just an ugly band limited sawtooth signal multiplied by the envelope. Now let's add the reflections to it. You can see that it changes the character of the sound rather significantly. It also changes the width and depth of the signal. It changes the transients, and it changes the timbre a little. That's what happens in the natural space as well. First, let's try to make something that is kind of close to what is present in this picture. Yeah. Here's the level of the input signal. You can see on this VU mirror. Probably I should take a bit different one, but nevertheless, at least it shows some numbers. We have input signal bouncing around at -20, yeah. And let's now check the reflected signal. Yeah, something near this level, yeah. 0.4, yeah. The first one was 0.4. Yeah. And let's add this one at 0.4. Yeah. Now, level-wise, Gressinger talks about something like this, yeah. But there are also other parameters that acousticians use to describe, to characterize this part of the impulse response. The first one, which is usually used in a place of early spatial impression, is ASW, or apparent source width. David Gressinger doesn't like this parameter for its semantics, but nevertheless, people use that. It's a subjective parameter. It characterizes how people perceive the width of the sound source. Yeah. Its objective correlate is interaural cross correlation. Yeah. So in three-dimensional sound field, that means the difference between the signals coming to the right and left ear. Yeah. If we will take a stereo recording as an example, then in my case now, the cross correlation between the left and right channel is the same thing basically. And we can see that now we don't have that much cross correlation going on because it's almost dual mono. Now, the recommended value for the interaural cross correlation for the good concert hall is around 0.5. It's something between 0.4 and 0.6 usually. So, for the same level, we should have more cross correlation, more difference between the left and right channel, which would be closer to the good concert halls. I can do that here with this NDEF GUI by using this send button. What it will do, it will send all those parameters for the underlying synthesis node, at the same time recalculating all the differences that I put inside of the function for the NDEF itself. I will explain this thing a little later. Just want to show the functionality of the tool first. So if I place this send thing, you can see the character changes a lot. Yeah. So this is a bit closer in a cross correlation values to what we talk about. Of course, we can go further. Now the question is, what is the level? We see that reflected sound is now much bigger. And we can also play with the delay times a little. So as you can imagine, in a real space, not only every seat will have different values for those parameters. Every note actually will have a bit different parameters. I'm using this rather ugly signal just to show the instrument itself. Of course, it will behave more gently for the real musical signal. In the real concert halls, we don't hear this type of signals because every signal, the first thing is generated with a lot of noise. but then goes through the resonators of the instrument, and so becomes rather more smoothed out than just a sawtooth signal multiplied by the envelope generator. Now the equalization effect. If we minimize the delays, if we minimize that internal time delay gap by scaling the delays. This is scale delays. The name of the parameter is scale delays. It just GUI specification kinda has a fixed number of characters, so the name doesn't fit. Didn't find yet how I can play with that. Now we can see the sum of direct and reflected sound is almost indistinguishable in time, yeah. But the timbral effect is very pronounced. And we can make it even, the reflections even louder compared to the dry signal. And thus we can play with the width, depth and equalization at the same time. And by playing with the Q, as you can see, we can introduce rather significant difference. Yeah. Now, you can see what it's doing. Yeah. Now by changing the resonance profile, we can introduce big changes. This is why I like this instrument a lot. This is the instrument that you won't find a lot in a commercial area. Maybe because it's very simple to do, to build this thing. But this is the thing that is usually used by mixing engineers to provide depth and width. Because first thing is very natural. You don't do those moving delay lines, yeah, modulated delay lines. It has that reference to the natural acoustics, and at the same time it can bring dramatic changes to the sound without adding some extra sound images to the picture. This is the thing that is very much desired usually, especially in a dance mix. I don't mean dance mix, yeah, where we have a lot of phantom sound objects. We can control spread by multiplying the pan values by this spread control. If it's equal to 0, we get the double mono signal. If it's equal to 1, then every parameter is sent as it is, and the -1 will change the pannings. Yeah, and more than that, we can pan the whole data reel, like bias the whole set of the controls to the left and right, and so defining kind of the re in a stereo field for the certain instrument. What else? Yeah, let's make the delays bigger. Now scale delays just gets multiplied by every delay value. So if it's smaller, that means the delays are smaller. Yeah, all the delays. Not only internal time delay gap, yeah. If it's bigger, then the distances are also bigger between every adjacent delay. Now you can see that at this point we can distinguish between the dry signal and the reflected one, even though they are related to each other as belonging to one stream, one auditory stream, but we can distinguish between them. The effect of distinguishing between those original and delayed sound is called the Haas Effect. by the name of the researcher who described it. The effects, the description of that effect says that if the delay between two signals is less than 50, around 50 milliseconds, a little depends on the transient character. If it's less than 50 milliseconds, then we start to perceive those two as one. But the one which is later will specify like to which direction the extension, the spatial extension of that signal will go. Yeah, let's take a look at this thing. Now by default the internal time delay gap is 20 milliseconds. Now let's multiply that thing by 2 and a little more. Now we hear them as two different signals, yeah, two separate ones. But we understand that the second one is related to the first one, yeah. It's a kind of a processed variant of it. And that's very meaningful in a musical context, yeah. What that does, it changes the dynamic range. Like diminishing the internal time delay gap and making the reflection part louder allows us to play with the timbre, and in particular to emphasize the middle frequencies by using the filters. Yeah, this is a very important task in the sound recording usually, because middle frequencies are the frequencies that will be reproduced better by the most stereo systems that listeners will have. Yeah, not low and high frequencies, the middle frequencies is the key. And by lowering the internal time delay gap and playing with the amplitudes of the reflections, we can do that in a rather natural manner. Increasing internal time delay gap allows us to feel the space between adjacent notes, musical notes, and this changes the dynamic range. Yeah, it makes the overall feel of the instrument louder. Yeah, and people usually do that, and musicians usually do that in particular by using what is called slapback delay. Yeah, and it's kind of this. And if it's too harsh, we can filter out high frequencies. Yeah, or we can play with the bandwidth, the filters. Yeah, and of course by using different resonance profiles we will get a bit different timbres. Yeah, now that I hope I explained the functionality of this tool, let's take a look at the source code. The source code is very simple. I get an input signal, yeah, and I want this signal to be mono. One of the important things, as David Gressinger talks about it, is to use amplitude panning and not phase one in this case, because he wants to get bigger separation. He wants to get the wider sweet spot when the person will listen to this recording. Of course, he actually talks about not only stereo field, he talks about 5 channels, he talks about putting the signal of interest to the middle channel, yeah, and so on, and about some microphone patterns. All that's okay. I'm talking just about the stereo configuration. And the thing is, as he puts it, the amplitude panning is better. That doesn't mean that we cannot use any other methods. For example, I have a stereo input, yeah, and I want to keep that stereo image with the reflections. I can use not the pan 2 as you can see here. I can use balance, for example. So I sum the input signal in order to be mono. Then I calculate the delays So we have an internal time delay gap, 20 milliseconds, plus I, which goes from 0 to 5 in this case, multiplied by a random number between 4 and 7 milliseconds. Yeah. So every next delay time will be 20 milliseconds plus 4 to 7, then plus 4 to 7 to that, then plus 4 to 7 to this, and so on. Yeah. Multiplied by 1, 2, 3, and 4. And first one multiplied by 0, so it will be just 20 milliseconds. Then those values get multiplied by the scale factor, and then we get to the filters. The low pass filter is a one pole. I think it's the best one to be used in the reverberators, and not only in the reverberators. This filter is very gentle when used in mixing. For example, it will smooth out high frequencies in a very natural first order filter manner, 6 decibels per octave. For the lower part, HPF, it's a second order filter. Yeah, I guess. Yeah, it's a second order filter. What the fuck? Works beautiful. It's okay. We can, as I already said, omit them, but it's so cheap thing that what's the problem with it? Let it be here. The next thing is, well, as usual, and you can see I always use those loops and arrays here. It's a nice way to deal with this type of stuff, which is kind of scalable. Yeah, it becomes scalable. So I can put not 5 but 10 or 15 here, and everything will work. Yeah, but of course in this case I would probably remove all those KRs, and you can see that the code itself here is a bit ugly because the symbol class doesn't have a concatenate mechanism. This concatenation returns string. Yeah, so I have again to tell as symbol, convert that string to symbol to make KR. But nevertheless, this is the method that you can use. I use it because I don't see any other, but it allows me to create a bunch of controls, formalized controls if I want to. In actual sense, I would just leave this thing and remove that stuff. I will show later that example. Then it goes through the filter. The filter frequencies are calculated with this exprand from 300 to 2000 Hertz. Again, the frequencies of interest are low, mid, and high mid frequencies. And as you can see here, I make every next reflection to be quieter, yeah, to have lower amplitude by dividing it by 1 plus I. Yeah, for the first iteration it will be 1, so the original amplitude. For the second one it will be half of that, then half of that, and so on. So we delayed, we filtered, and then we pan that stuff. And the pan values calculated, well, now with the control signals, but actually should also be done as I usually do it. That's why I say should be done with the random number generators. And the end is we just mix input and panned reflections. Since pan 2 returns stereo signal, which is an array, yeah, array of 2 elements, this array will actually have 5 2-element arrays, yeah, array of arrays. So when we sum that stuff, we get stereo signal, array of 2 elements. So that's all about it. The construction is very simple, and you can of course play with the resonances, maybe a bit different distributions. You can play with the Q values, and of course with the delay times. Now for the delay times, as Leo Biranek says in his work, the delay times for the early reflections pattern should be with the close intervals but not same intervals. Yeah, actually the key task is to make a non-periodic sequence. The good method to make that non-periodic sequence is to use a set of prime numbers, of different prime numbers between each subsequent delay. Yeah. So here's an example of a pseudo unit generator which can be used in a manner like this. You see, just like a unit generator that does all that reflection stuff for us. So here's an example in which I have prime delays which for the sampling rate of 44.1 kilohertz will be around 4 to 7 milliseconds. So I specify this array, and then here, after the creation of empty delays array, I specify the delay offset as an argument to the function, to the method. Yeah, actually. And then what I do, every next delay is equal to the previous delay plus some prime number. Yeah, this prime number here is, first of all, this array is scrambled. Yeah, so it will always have a bit different set, and since I index it I will never get to any of the elements twice. Yeah, and then I convert it to the milliseconds by dividing it by the corresponding sampling rate that I wanted. Now after that I can scale that, no problems. I can scale that. I don't need actually the values to be prime. I just want them not to be periodic. Yeah, and of course, if to be like psychopathically mathematistic, you got what I'm saying, I guess. If we are not that pedantic, we can neglect the fact that the float calculations are not that strict and so on. Actually, no real concert hall has prime number delay times. It's just a good method around which we can dance and have fun. As you can see, I also clipped the number of reflections values because we don't want to have an error, because we specified more number of early reflections than we have in our prime delays array. So I click that number just in case, and then everything else is kind of same as it was before, but without the bunch of control signals. All the signals that we have here is the input parameters specified as an argument to the pseudo unit generator. Another difference is I sum it to mono again, but with some logic. Well, logic is very simple. If the signal has more than one channels, yeah, then I will sum it to become mono. If not, then I will leave it as it is. Very simple method. And in this case, the Qs, or the bandwidth for every filter, is calculated using this exponential random generator. That's all. That's it. Did I talk about everything I wanted to talk about? Temporal effect, yes, I talked about that. Liveness, I mentioned that. Apparent source width, I told about that shit. And what else? Yeah, I told about everything. And once we have it, we should put this code into well, better to the separate file, into this directory. Yeah. In my case, like I am on this Linux system, it will be in a home.local share Supercollider extensions. Yeah, once you put this code to this file in this directory and recompile the library, you can use it like in this example. Let's take a listen. This is a very synthetic FM generated sequence, percussive like. I had something, yeah, I should remove that first. Oh, sorry, not like that, like this, yeah. And let's put this periodic sequence. Okay, now we got an idea. Now let's listen with the reflector. By changing the synth depth, I can change the whole that reflection pattern, yeah. Oh, I like this one. I like this one. Reflector by itself. Sorry. Yeah. And now with the Pantu. Yeah. So every time I launch it, it's not the same, like it will be different. By combining this method with the control of the random number generation through the seed numbers, through the current thread seed number, we can fix the example that we have and then return to it and use this thing not only for the stuff we generate using Supercollider, but also for the recordings that we work on if we mix something. Yeah. We can, in this case, in a Linux, and that's basically why I like this system more than, let's say, Mac or Windows for this type of stuff, is that we have this jack-D process system that allows us to commutate, to interconnect all of its clients, the programs, inputs and outputs between each other. So I, for example, usually do stuff like having a digital audio workstation, then making some send from the certain channel to a certain Supercollider input, process it, and then record to a new track. Well, in the same manner as you would do with the hardware. That's what I do a lot. But since this instrument is very useful and probably should be always under the hand when you mix something, I should probably make a Faust code for that, and I will probably add that with the next video, in which I will continue on this reverberation profile and I will speak on this statistically analyzed part of the impulse response. Should I talk about the generation method itself? Probably there is nothing new besides that the frequency is specified as a sweep, and sweep is the thing that we always need, not always but usually need if we want to make a percussive sound. Other than that, it's all abusing the same methods that I was talking about in the previous videos on FM, so there's probably no need to do that. But later, actually, I will talk about the percussive instruments generation. Yeah, no, yeah, by I will talk on the synthesis of the percussive sounds. Yeah, all those snare-like, kick-like, hi-hat-like, and all that stuff. And I will touch on the modulational synthesis methods for that. I like them a lot. And other ones. So this is a subject for the future videos. That's all for this first part. That's all. If you have some questions, put that thing onto the video. Till next time.